Let me know once you can see the screen.
Yeah, we can
Yes,
see
sir,
this.
we can see your screen, but your voice is a
Yeah.
little low.
Okay. Hello. Yeah, is it better now?
Yes, sir, yes.
Okay.
And people are able to hear on the in the class.
Pinaki, please confirm if students are able to hear in the class.
Audible?
Yes, yes.
Yes, I got it.
Okay,
Okay.
let's begin.
Great. Yeah. Can you start it? Okay. Fine. Okay. Yeah. Hello, everyone. So let's continue today from our last class. In the last class, yeah. So I just outlined what we plan to do today. So I'll just do a small recap of what we did in the last class to set the context for today's talk. So today, the main agenda is to talk about transformers. And so we'll look at an introduction of transformers, motivation, and then deep dive into transformers. And this is a very important topic. So that's the main agenda for today. And then we'll talk about further reading. And I think we also need to discuss the assignment today. And if time permits, there are a few small topics which were got left out last time, if possible. Otherwise, here you have the notes. Yeah. So again, just ask me at any point if you have any question. Uh, I don't have access to the chat, as I said, so just ask out the question. Okay, so let's quickly do a recap of what we did last week, right? So we focused last week. We started with looking at tasks which require processing text sequences, sentences, paragraphs, documents, whatever, right? So sequence of words or tokens. And we looked at language modeling, which is a very fundamental task to NLP and particularly to modern NLP. We looked at sequence labeling tasks. So sequence labeling tasks are where the input sequence and the output sequence have the same length, and there are categorical output, financial of categorical outputs, right? So this is a task like, say, part of speech tagging or named entity recognition. Then we have sequence to sequence tasks, in which the number of input sequences and output sequences, sorry, the length of the output sequence and the length of the input sequence may be different. So there is no one-to-one mapping. And so that's a more complex task, and many tasks in natural language processing fall under this category. In fact, it's like a general uh, input-output category. All kinds of tasks can be modeled as sequence-to-sequence tasks. So machine translation is an example. Summarization is an example. Right? So in machine translation, you have a sentence in one language going to a sentence in another language. Word order can change, uh, and the words can be deleted, inserted, etc. Right? So when it comes to summarization, the output text will be much smaller than the input text. So there's a lot of variation in this kind of task. And we looked at how we can model all this class of tasks. So we started with feed-forward language models, and we looked at their limitations. Particularly, they cannot handle uh, variable length context. Uh, so then looked at RNNs, which are a way to model variable length context by modeling some state which captures the previous input seen. LSTMs are a variant of RNNs, which have better learning characteristics. And they prevent problems with optimization, with vanishing gradients and exploding gradients. So we saw that. Then we looked at encoder-decoder models, which are essentially conditional RNNs or LSTMs to be able to solve sequence-to-sequence problems. So just RNNs or LSTMs by themselves can do sequence labeling kind of tasks. To do sequence-to-sequence problems, we need encoder-decoder models. So we have an encoder RNN or an LSTM, which takes in the input, encodes it into a state. This state is used to initialize a decoder, which is a target LLM, and that generates step by step. Right? The one major limitation of this simple encoder-decoder mechanism is that the source context is used to just initialize the first state of the decoder, and by the time you generate it, sort of starts forgetting things. So, and even if you put this, feed the source context at every time step, still it's not relevant to the input or what is being generated at any point of time. So we looked at attention mechanism, which was again one very important concept. So here the idea was that, okay, at, at every time step, the decoder sees what is important at that point of time. And this is done by sort of doing a weighted average of the source vectors, source set vectors, right? And the attention mechanism is all about learning how to give weights to these each of the source tokens. And we found that this is a very strong method to sort of address uh, not forgetting the source, to address word order changes in translation and so on. Right? So very, very, very fundamental concept. And today we'll see that attention is actually far more important than what we even saw last time, in the context of transformer models. So any comment at this point, or anything you want to clarify from the last class before I move ahead? Okay, then let me move ahead. So today we will talk about the transformer model. And this is a model that has kind of revolutionized NLP and AI. And the work came out in 2017. The paper was named "Attention is All You Need." So as you can see, attention is involved here. So this is the paper from Google Research, or Google Brain rather, with Ashish Vaswani as the first author and a bunch of other folks. This is one of the most widely cited papers now. It has already 200K plus, 20,000 plus citations. And the reason it is so revolutionary is that it has made AI more scalable. It showed a way of building complex system from very simple building blocks, and how do you put together these simple blocks in a scalable way. And the result is that this underpins all NLP models today. All the revolution that you're seeing in large language models and AI today can be traced back to this work. So uh, you take any language model. 4 or 5 years back, you had models like BERT, then GPT series came out, and then every LLM today, Claude, Gemini, any translation models, all of them are based on transformer. Right? So it is the kind of it is what underpins today's NLP, and therefore this is very important for us to learn. And even outside of NLP, right? So transformer has revolutionized the whole field of AI, right? So the vision transformers, there is AlphaFold work from uh, Google DeepMind, which again builds on transformers, and many other works. I mean, this is just a sample listing, but uh, a lot of work today is built on transformers, and therefore uh, it's absolutely a very fundamental topic. A lot of the cutting edge work is based on a deep understanding of transformers. And therefore, what you should aim to do, and what I'll try to do in this class, is to start off that journey, is to understand the ins and outs of transformers if you want to really get deep into NLP and AI. There are lots of resources available to build on what we'll start today. And that the main takeaways to for us today is to get the fundamentals right, and then uh, you can delve into many, many details. Okay, so let's put transformers in the context of what we have learned so far. Okay, so what we did so far is, as I said, sequence modeling approaches. We have a feed-forward LLM. So in a feed-forward LLM, what we have is a fixed context. So you sort of say, in this case, there is a context of three. So the three words that are their embeddings are concatenated together and fed into a feed-forward layer, and then used to predict the next word, right? In an RN and LSTM kind of language model, we don't do that. We use a recurrence relationship, and the entire context is modeled as a single state vector via recurrence. So every function, every output is a function of the state and the current input. And so that's a recursive definition, right? So the current state is a function of the previous state and the current input. Okay, so this allows you to kind of model infinite context, whereas for feed-forward LM, you're bound to kind of uh, address only a finite context. Okay. Now, But RNN and LSTMs are not without their flaws, and we'll come to that. So there are very long dependency paths. Okay. So you are defining a recursive function. So the first token impacts the kth token via a long chain of intermediate tokens, right? So I read and then and then impacts book through a long sequence. Now that is a problem because if you try to optimize this, the gradient flow is very weak. And there are, of course, solutions like LSTM which try to address that. But still, fundamentally, you would want that you can make a more direct impact on the tokens than going through this entire sequence of uh, recurrence relationships, right? So that's a major limitation. This long distance dependency. It also has another implication. These models are sequential by nature. So if you want to generate, if you want to process the kth token, you have to process the first k minus 1 tokens before you can process the k, because the state is always needed. And that is a fundamental limitation to how fast you can process text. And finally, the context is this is unidirectional processing. You look at context in one direction and then keep generating the next state, right? So if you want to look ahead, say a word depends not just on its previous words, but also the future words, then there is no direct mechanism. Of course, what people do is you train LSTMs in two directions and then concatenate the state vectors. That works well, yes, but it's kind of an afterthought. It's not built into the design. Okay, uh, so these are major limitations of RNNs and LSTMs, and uh, let's see how that can be overcome using ideas from attention. Okay, so as I said, the RNN state vector is a representation for the entire context. Okay, one single vector for the entire context. Now we saw uh, in our class last week about attention. So attention is also doing something similar if you think about it. So although it's in the context of encoder decoder, so there is a decoder which is attending over the encoder representations. Okay, uh, but it is also building some sort of representation of the source. But what is the difference? It's not uh, building a single. It isn't blindly building a single uh, vector representation of the source. Okay, what it is doing is it's building some sort of weighted average of the source sentences. Okay, uh, but it's looking at some other sentence, the source sentence. But can we use the same idea, right? Can we use the same idea of attention, of kind of focusing on different parts of the same sentence to build its representation for the current word? Right? So because you're looking at the same sequence, this idea is called self-attention, right? And so that is the key idea behind transformers. Let's look a little bit more about what self-attention is. But remember, yeah, this is the most important idea that the transformer introduces. Okay, so in a very simplistic way, the way you can think about it is this. So now you have replaced this whole recurrence mechanism by a attention mechanism. So which takes in all the words. Now we already know what attention does. It does a weighted average of the inputs. Right? So the context is now captured by a single summary vector via attention instead of via recurrence. Okay, and now when you do it via attention, this long dependency chain is not there. Every word directly impacts the output word. Every input word directly impacts the output word via the uh, weighted averaging. So that is the key idea, right? I mean, so if you compare it with the feed forward block, it's like you have all these words fit in. You are concatenating it in feed forward LM, and therefore you are limited by the context. Here you are creating one single output vector, but it's just a weighted average, so the dimensionality does not change. Yeah. So yeah, remember that this is one important idea for you to take away. And let's recap what attention was doing before we delve into self-attention. So what did we do in attention last time, right? So so here you can see the encoder states E1, E2, E3, E4 for every token on the input side. And what you do is essentially your summary vector for the encoder C1 at the decoder time step 1 is a weighted average of the encoder vectors. And these weights, Aij, are essentially uh, learned by looking at the similarity between the state vector, and this state vector is what is called the query, right? So some query and its similarity to the keys. So E1, E2, E3, E4 are the keys. So how similar the state vector, the query is similar to the key, and that's what you compute. And once you compute that similarity, then it's sort of that weight is used to average the values. So the values in this case are also E1, E2, E3, E4, but the queries and the keys and values can differ. They can be different vectors. In the case of standard attention mechanism, the query is the state vector from the decoder, and the keys and the values are the encoder states. They are the same. Okay. Right. So yeah, we saw that yeah, we're just reducing the whole encoder uh, set of encoder vectors into one contextual vector. Okay, now what? Let's compare that to what self-attention is doing. So here, what you're doing is you're capturing the context using a single summary vector via attention again. But now the attention is not over some other source word, but the same over words in the same sequence. So I read the book, right? So you attend to the words in the same sequence. And if you see the diagram on the right side, that's a better representation of what I want to show. So this, if you look at this here, these arrows show show what words contribute to building the representation for uh, the words on the tops, right? So the words on the top and the bottom are the same because they are from the same sequence. Uh, but okay, you are attending to the same words, but how is that possible? You don't have. How can you build attention? Do average of representations of the same word that have not been built, right? So the idea is that, okay, you look, this is typically for deep neural networks. So you look at representations from layer I and use that to compute representations for the next layer using self-attention. Okay? So that's the key thing, right? I mean, you're moving from one layer to another using attentions. And so let's look at the word I, right? So I is a weighted average. The representation for I is a weighted average of uh, the representation for read the book, right? The other three words. And similarly, read is a weighted average of all the other words. Okay. So what are we doing? So this is a way to sort of obtain contextualized distributed representations, right? So at the end of this process, you're going to get some representations for each word, which is, and every word is now defined by its context. And that's why it's a contextualized representation and dynamically contextualized, right? So every sentence, you apply this attention mechanism, you get a uh, uh, different representation. Now, in that regard, this differs from what you have seen with word embeddings, right? So with word embeddings, you get some representation once, right? So you train the word embedding and it's frozen. That's not the case here. Here, the same word read can have a different representation depending upon what context it comes in. And that's why I call it a contextualized distributed representation. And this is how it differs from what you have done in word embeddings. Okay, now how does this address some of the problems we just talked about, right? So now the dependency path length is minimized to one. So I is directly impacted, directly a function of read the book, right? The representation for I is a direct function of all these words, and similarly for the other words. So the whole dependency chain is gone. Our modeling is much more simple. And now, if you look carefully, all of these uh, word representations can be computed in parallel. These are all weighted averages. So weighted average for I, weighted average for read the book, all of them can be done in parallel, given you have representations for the previous layer. So once you have computed layer I's representations, all the token representations for layer I plus one can be done in parallel. And as you can see, bidirectional context is just modeled naturally, right? So here you can look at the entire context, left, right, and build the representation for each word. So in that sense, that limitation is also overcome. Models can be more interpretable, and this comes back to attention. So what is attention doing? It is looking at what weights to give each of the sources. So weights are some sort of interpretation of, okay, read, how similar is it to say the or book. So you can have some sort of interpretation, and there are lots of studies which have used attention to do different kinds of interpretation studies. So I hope that is clear. I mean, so here the idea with self-attention, to summarize, is that we are building these distributed representations in parallel and along the whole sentence, and we have reduced the dependency to just a single path link. So this is what is the single most crucial factor about transformers. Okay. And that's why the paper asks the question, okay, is attention all you need? Because it has done away with recurrence. And attention is now the mechanism to generate representation, which is what one of uh, one of the most important functions of any neural networks. So yeah, but it's not just that you do this self-attention and that's done. There is quite a bit of machinery and trick to get this to work together at scale, and that's what makes this paper so rich. A lot of experiments. Maybe they've experimented with tons of stuff to come up with this final architecture that works. It's all highly empirical, but there is a reason why each of these blocks are the way they are. Okay. So what is this architecture? So let's first do an overview before we delve deep into each of these blocks. So what you see on the left-hand side is the uh, architecture for the transformer model. Okay. So the transformer model is an encoder-decoder model for sequence-to-sequence modeling. And it's a stack. It contains, so it's a deep neural network. So on the encoder side as well as on the decoder side, you have multiple uh, layers. Okay, and so here on in this diagram, on the left hand side you see the encoder, on the right hand side you see the decoder. So there are n such layers on say both sides. So you can have n encoder layers, n decoder layers. Okay. So the encoder and decoder model blocks are largely similar. So we will look at some common models, and then we will look at uh, some couple of specific things to the decoder module. Okay, now what what is each of these layers, each of these blocks, right? So these are blocks stacked together into multiple layers. So each block combines a self-attention, some kind of self-attention and feed-forward modules. We'll again look into details about what these are, just to give you some key ideas which we'll delve into. So the model has something called multi-head attention. You'll see that here, positional embeddings, uh, layer norms, and residual connections. So these are all things that have been put together into this package to make a very powerful uh, learning machine. Okay. So let's look at how is self-attention done. And this is very straightforward if you have already understood what attention does, because there's nothing really new uh, in the attention mechanism in encoder decoder. You are attending to the source words. Now you are attending to the other words in the same sequence. That's all. Okay. But yeah, just some terminology and concepts. So we have for every word I, we compute its query key and value. Right. Uh, so as I said, like there is, say, if you're looking at word xi and computing its representation. So xi is the query, but in the case of the transformer, it's not directly the query. It is sort of transformed by a matrix WQ to generate the query QI. Similarly, the key vector is generated uh, and the value vector is generated by using three different matrices. And now once you have this query key and value, you know how to do attention. So first you sort of compute the similarity between the query and the key vector, and then convert it into a probability distribution using softmax, what you typically do with an attention model. And then now you take the value vectors and then do a weighted average, weighted by the attention weights that you learned. So that's it. I mean, standard attention, just that it's applied to the words in the same sequence. Now these three vectors, WQ, WK, and WV, these are new parameters for the model. And they allow you to look at the same input xi from three different perspectives, as query, as uh, key, and as value, right? So the model is transformed, the model transforms the same input vector in three different ways, playing three roles. So one little difference that this particular paper does is the way it computes the uh, similarity, the dot product between the query and the key. So it doesn't, so instead of just doing a simple dot product, it does a dot product and then scales that by the square root of the dimensionality of the vectors. And this they found was important to avoid the dot product taking very extreme values because its variance becomes large and training becomes very unstable. This is always a consideration when you're doing very deep networks, and this helps sort of prevent it. So that's the like little detail in here. Otherwise, again, it's standard attention. Okay, now what do we achieve by doing this kind of self-attention? So these are some visualizations of attention. So what these plots show are a sentence, and then uh, at any point, what are the words it is attending to? Where are the attention weights mainly focused? So if you look at the sentence, the example on the left side, you'll see that the making has a strong connection with more difficult, right? And so this is a little bit far off. It's a dependency relationship, but it's not adjacent. And self-attention is able to capture these kind of dependency relationships. On the right hand side, if you see the word it's is has a strong attention weight with the law, right? Essentially, which is it's an anaphora resolution. So it refers to law, and the attention module is able to kind of detect this. Right? So the model essentially learns to focus on the right context dynamically when processing a sequence, which is what you want the attention module to do. Okay, now there is a concept of multi-head attention, right? So we understand what attention is, what self-attention does. But as we just saw, there are different kinds of relationship. There is dependency relationship, there is anaphora, there might be many other relationships, different kinds of structural relationships, adjective, noun modifier, or any other kind of relationship, right? So verb and noun relationship, or there can be semantic relationships. Say what is the semantic similarity between two words. So there are lots of things to capture. Uh, so can the model be rich enough to capture different kinds of relationships? And so one head may be focusing only on one word majorly, right? But if you use multiple heads, uh, uh, then you can capture multiple relationships. So what does a head mean? So a head is simply multiple blocks of attention layers, right? Uh, so in this we have multiple such attention uh, layers or attention modules at the same layer, capturing different aspects of relationships. And the way it is implemented is, so you have one, attention head two, attention head three, four. So each of them have their own WQ, WK, WV parameters that we just saw, which generate the query key and value vectors. And the way you do it is, okay, you feed the input vector coming from the previous layer into the attention head, and the output of the attention head is a lower dimensional vector. So if there are four attention heads, then each attention head will generate d by 4 dimension outputs. And then these are concatenated to to generate the final output vector from the multi-head attention layer. So each of these heads is a self-attention module, and then their outputs are sort of concatenated and to kind of get back the original dimension. So what is the impact of this, right? So this is again another example. So here the word it mm, sort of, now there are two heads. One is the orange head and the second is the green head. So in the orange head, it's sort of doing some sort of anaphora resolution only, right? Whereas the green one is sort of focusing on the relationship with the verb, right? So that's one kind of dependency relationship. So now having two heads help you capture two different relationships. So this makes the model more richer and in terms of the different kinds of patterns it can detect when it wants to build a rich representation for a token. Okay, so that was about the self-attention layer. So what the self-attention layer did was just was build distributed representations of words going from one layer to another. And so as you go from one layer of the network to another, you are building more in general, the understanding in deep learning is that you build more abstract and higher level representations. However, attention layer is very limited in its expressive power. What are you doing there? After all you're doing is simple averaging of vectors after a linear combination. Right? So the matrix multiplication is just a matrix transformation with the W vectors is just a linear transformation. So it's a linear operation. There are no non-linearities, and this is neural networks 101. So when there are no non-linearities, there is very limited learning. There are very few classes of problems that this kind of a network can learn. Right? If you remember the initial lessons from perceptron, you'd know that this kind of a network is very limited. So you need non-linearities in a network. And how do you have non-linearities? The standard solution is to have feed-forward modules, right? So in a transformer network, the output from the attention module is fed to a feed-forward layer. Actually, sort of two feed-forward layers, you could say, two feed-forward modules. Uh, so the first one, so you take the output from the output type from the uh, attention layer and then sort of apply it to a feed-forward layer, W1 into the output plus B, and then run it through a non-linearity, which is important, and then through another linear layer. Uh, so these two linear layers are applied. And the important thing to note is the first one, W1, is an up projection. So if the original dimension was D, the after projection, this might be n times D, typically around 4. It's no magic number. Every network is different, but some average, let's say, typically much larger than the input dimension. So which means you're adding a lot of parameters. And then you are doing a nonlinearity, and then you are down projecting it back to the original dimension. So when you're doing up projection, you're adding a lot of parameters, and this layer, the feed-forward module, actually accounts for a large fraction of the parameter budget in the neural networks. So, but it is also the layer that kind of, you could say, does a lot of the learning. So very important layer, and a lot of the parameters go here. So just to note, and you can look at the diagram on the left. So self-attention looks at the entire sequence at a time, and generates a representation for each token, right? And that's what weighted averaging is all about. Whereas the MLP is looking at only one token at a time. So it takes for every token representation from the self-attention layer, it is applied independently. But the set of parameters are the same. It's not like every position has a different parameter. That won't work, right? So there is one MLP which is applied to every token. And again, this can be applied in parallel. So this architecture is parallel even at the level of the MLP. And MLP is just matrix multiplication, which is highly parallelizable. So again, okay, now there is a problem with this network though, this architecture that we've seen so far. This has no structural or positional awareness. Sorry. So let's take a couple of examples, right? So if you take the sentence, the dog barks at the man or the man barks at the dog, the representation of the dog will be the same, although their roles are very different in the two sentences, right? Because what did you do? Self-attention, weighted average. So weighted average at any position will result in the same output, right? And similarly for man, right? So this is not able to distinguish the roles of the two words, of the same word at different positions. The next example, if you take something like the old boy taught the little boy. The two boys have two different roles, right? But because both self-attention and uh, the feed-forward layers, they are sort of invariant to the position, the representation is the same. Now, this is not uh, sufficient, right? In language, every position has a meaning. There is a structure to the sentence. And so how can we sort of capture this kind of a structure uh, in the modeling? Now, when we were doing LSTMs and RNN, it was implicitly captured because you were moving from left to right, and the context was a function of the previous words, 1, 2, 3, or 4, whatever. And depending upon what words came, the state would change. So it was implicitly modeled, but that is not modeled implicitly in the transformer model. And therefore, we have to do something explicitly. And that something is what is called positional embedding. So this is a very standard thing in all transform models. So we need to generate some sort of representation for every position. So position 1 is unique, position 2 is unique, position 3 is unique. So one way to do it is you can have an embedding for every position. So these are called positional embedding. So position 1 in a sequence has a specific representation P1, position 2 has a representation P2, and so on. Right? And so uh, when you start processing a sentence, you get the word embedding, and then you add the word embedding to the positional embedding. So the same word at two different positions now will have two different position encodings, because the position encoding is position specific. T1 has a particular embedding, T3 has a particular embedding. So even if the words are the same, their final embedding after adding the two things, after adding the token embedding and the positional embedding, will be different, right? And this is the embedding that is then fed into the transformer layers. Okay, so addition is just one choice. I mean, you could have concatenated, but the dimension would have changed. This is what is simple to implement, and this is what was chosen. Now, how do you model these uh, embeddings, these positional embeddings? One way to do it is, yeah, these are also additional parameters. I mean, these embeddings can also be additional parameters, and that is what is called as learned embeddings. Okay, so when you train the entire network, these embeddings are also learned. So the, the model will learn to have unique embeddings at every position. Okay. And therefore, typically, yeah, you would have some sort of max length that transform models can process, because you need to have positional embeddings for every position. Otherwise, there is no real need to limit the sequence length. Right? So, but it's positional embeddings that limit the sequence length. So this is one way of doing it. Another way of doing it is what are called sinusoidal embeddings. This is what the original transform paper did. Here you can define the entire positional embeddings. This is a this is not a learned embedding. This is just defined based on some sine and cosine functions. And if you each component is some sort of sine and cosine function, and it just varies in yeah, some of these parameters, and you'll see that this will result in a unique embedding at every unique position embedding at every position. And so this is good because, yeah, you can, without learning anything, model this. Okay. Now, fine. So this was another important concept. So because transformer inherently has no way of representing structure, you encode positions, add them to the words, and get the position embedding. So now this is, of course, an approximation. You're not really capturing any structure, but you're just differentiating positions, and turns out it's works pretty well in practice. There are limitations to this kind of position embeddings. For example, if you want a very large context, if you know the large language models today, they have, say, 1 million context. Will you have 1 million position embeddings? No. So there are new kinds of position embeddings like rope, which are relative embeddings and all. Let's not talk about that today, but you should know about it, and I'll share some reading references as well on that. Okay. So yeah, with this, we've covered the most important concepts when it comes to transformers. Uh, so we have looked at the blocks that I have circled in red, right? So we have looked at all this. So we looked at multi-head attention, and we have looked at input and output embeddings. Well, we didn't look at it, but that's standard. Position encodings, we looked at it. So we've done all this. Now let's look at the other part. So now the multi-head, feed-forward, and the other things, all of them are kind of stacked into multiple layers. And similarly, on the decoder side, where there are a few new things which we'll see. So what are the new things for us to see? So let's look at the decoder side of things. So whatever we saw so far was on the encoder side, but also was applicable to the decoder side, feed-forward and all. But there are a couple of things that are different on the decoder side. So what are those differences? Okay. So difference number one, So the decoder all has to have self-attention, of course, to construct its own internal representation, but it also has to look at the encoder, right? So in an encoder-decoder model, the decoder has to look at the encoder. Okay, and therefore you will need an extra cross-attention module. So the one I have marked in blue, and if you see the arrows, so it's attending to the source, the encoder side, right? So this is a multi-head attention on the source side. This is a cross-attention module, an attention module between the encoder and the decoder. Similar to self-attention, the only difference is that this one looks at the uh, top encoder layer instead of the previous decoder layer. That's all. But otherwise, the mechanics are the same. The second difference is the very nature of decoder, right? So decoder is a generation module, and at inference time, when you're generating the output, it has to go from left to right, generating one token at a time, and therefore at time t, it knows what words had been generated in the past till t minus 1, but it does not know the future words, right? And therefore, bidirectional context is something you cannot do. You should not do, otherwise your learning is all wrong. If you use bidirectional context, future context on the decoder side during learning, you will go wrong, right? So you cannot compute attention, self-attention using the future values. And so what you have is a masked attention. It's just a simple modification of self-attention. All you do is, yeah, when you compute the attention heads, you don't look at the future tokens, only at the past tokens. Uh, and yeah, the key thing is, I mean, instead of kind of a naive implementation where at position k you have construct a matrix for only the previous k minus 1 words, you can still do the entire matrix multiplication, but then just mask out the future tokens, right? By setting their attention functions to minus infinity. Right? So if you do that, you can do this computation sort of in parallel again, and get the advantages of parallel processing. Okay, so those are like the key ideas that we have covered. Now I think there are a couple of things related to training deep networks that we need to discuss. But I'll pause at this point, and if there are any questions, I think this is a good time to ask. Any questions, any doubts?
So, Anoop, I've seen that the students get a bit of confused when it comes to the parallel processing.
Okay.
So, on that, if you can spend a little more time again.
Okay, sure, sir. So let's go back to for initial ones. So there are multiple places at which some sort of parallel processing is happening. So let's first look at yeah, the parallel processing in the self-attention layer, right? So let's say I want to compute the representation for the word I, and we already saw that. So we already know the representations on the previous layer. So we are computing the representations layer by layer. So layer by layer processing is sequential. So you complete layer 1, then go to layer 2, then go to layer 3. So there is no parallelization there. But at the same layer, you can compute the representations of all the words simultaneously. So how is that done? Uh, so now the representation of I is a function of representation of all the other words, right? And these are already computed, and all you have to do is a weighted average of these, right? So you have to compute the attention weights, which is a dot product between the I, which is the query, and each of these words read the book. So all these dot products can be done simultaneously. Once you do the dot products, get the attention weights, you have to do a weighted average. And the way you do for I, you can do for read at the same time, right? Because the read representation has no dependency on the representation of I at the current layer. It depends on the representation of I only at the previous layer, which you already have. Right? So therefore, you can compute the representation of I, the representation of read, the book, all of them uh, kind of in parallel. And if you look at the way it's mathematically represented, and you should do that, if you read to the paper in detail. These are matrix multiplications, right? So, and matrix multiplication again can be parallelized, etc. So this is the one of the more important parallelizations that can be done. Uh, Similarly, yeah, we looked at this one, right? So again, you have multiple attention heads, right? Now these attention heads are also independent of each other. So you can do the attention computation for each head again independently. So there is no dependency. They have their own parameters and they're all processing independently the inputs. So you can do them again simultaneously. And the benefit of all this is that the entire sequence can be processed much faster than you can do with an LSTM. With an LSTM, you would have to do the first word, then the second word, then the third word. Once you finish this layer, then again on the next layer, you have to again do first word, second word, third word. And so it would be very, very slow. Here it's blazingly fast because all of them can be simultaneously computed. And we just talked about mm, the last point, right? Yeah, even on the decoder side, even though yeah, you want to mask you don't want to consider the future words. There is a trick by using these attention uh, uh, scores as minus infinity. You can still do all the attention computations, which is just matrix multiplication in parallel. And then because you're using this mask, you will it will automatically turn out that these values will have these future words will have probability 0, right? So j equal to minus infinity, right? Now when you're converting to a probability, you are doing a softmax. So exp raised to minus infinity, that will be 0, right? So future values get 0. So yeah, that's how the parallelization comes into the picture. If there are any questions, yeah, please go ahead.
Yeah, that's okay. That's okay now.
Okay, so let's then look at the final pieces to train deep transformers, right? So transformers with multiple layers. And it's always challenging to train deep networks, but over the years, like people have learned the tricks to train deep networks. So layer normalization, residual connections, these are not inventions that the transformer model has done. This is previous work, but incorporated in this architecture. Yes, sir, did you see something?
No. Right. Go ahead.
Yeah. Okay. So we look at the role that they play in the transformer network and what they are. Okay, so what is layer normalization? So the problem with training these networks is that uh, there is a lot of variance coming from the previous layer into the next layer. I mean, the network is the data is diverse, so the input is very varied. So the range of the numbers might be different and all. So in order to kind of have some sort of stability in training the network, in order to have some sort of consistency, what is done is after every layer, the inputs are normalized. So that you can reduce the variation by normalizing to zero mean and standard deviation 1 within each layer, right? And that sort of ensures that training is much more stable and much more faster. So that's the norm part that you see here in the network. So there is a add and norm block, and the norm part is this layer normalization. The add part is what will come to next, which is the residual connection. So, so far you've talked about everything in the context of a single layer, right? So the multi-head attention, feed forward, everything is in a single layer. The position embeddings typically are just at one layer, which is at the bottom embedding layer. Mostly, there are changes, some architectures where you have more complex setups. But still, we're talking about just one layer. How do different layers interact? So representation from one layer goes into the next layer. Now, what happens, right? Why is it so difficult to train these deep networks? What is the problem of vanishing gradients? It's the same problem that you saw with RNNs, but in a different dimension. So With RNNs, you have a long sequence, so going from one time step to another to the next, you lose. It's difficult to flow the gradients back. Now, the same problem when it comes to training deep networks, but now the dimension is the depth dimension. So, if you have to propagate the gradients back very deep, it's difficult. And also, typically, it's found that it's very difficult to learn very complex functions with deep networks. So there's a degradation in the quality of the representations. And so the solution is to both these problems is to add a residual module. So what is the residual module? So what you do is the output from every layer f of x is added back to the original input. Right? So the output from every layer is f of x plus x. So what this does is every layer is some sort of delta on the uh, original input. That's how you can visualize this or understand this. And so now what the network is doing is learning the residuals. So it's not learning representations at every layer. It's just learning what is the change in representation at each layer. And this is a much easier problem for networks to solve. And that sort of solves the degradation problem. Uh, then the way you solve vanishing gradient is because see the value x, the input is kind of directly being propagated layer by layer, right? So there's a direct connection between the bottommost input to the output. So that sort of helps the gradient flow. This is similar to what we did in LSTMs also, if you remember. So LSTMs, there was a direct connection between previous state, next state, and so on. Of course, there was some gating and all, which is not there out here. But the idea is the same. You have some direct path between the input from the across all the layers. Right? So that's what you get. So both with this residual module, you kind of get a solution to both these problems. So again, residual corrections is a previous paper, not an idea from this paper, but it was important to have a deep uh, network. Right. So now one very important update that happened. Right. So let's revisit layer normalization. So people found it very difficult to sort of train the uh, transformer network in a very stable way. And what after a lot of investigation, what was found out that this has to do with the way layer normalization is done, and a little change to the layer normalization made training much more stable. And so this changes between what is called a post norm and a pre norm. It is how and when the norm is applied. So in the architecture we saw just now, the original transformer architecture, we have a post norm uh, computation of the layer norm. So that means after the computation of the residual addition, then layer
Okay,
norm is
Anoop.
done.
Hello,
Hello?
can you hear me?
Yes, sir.
Oh, sorry. Yeah, go ahead.
Okay. So, yeah. So I was saying, yeah. So the original transformer module had this post norm uh, architecture where you do the residual and then you do the layer norm and so on, right? So going from one layer to other, the residual is sort of modified by the layer norm because the layer norm is now fed for the next residual computation. And this pe- people figured out is not a good idea because you are disrupting the original signal by adding these layer norms in between. And therefore, the architecture was slightly modified to take the layer norm out from the direct path and put it on this sideways path. So now the uh, original signal just travels as is, and the layer norm is sort of done before the feed forward module, uh, right? So that's why it's called a pre-norm. So whereas earlier it was being done after multi-rate attention addition and then layer norm, now it's being done before the multi-rate attention, and it doesn't, more importantly, it doesn't come into the path of the original signal. And with this, the training stability has increased. So all modern day transformers pretty much use the prenorm. There are some exceptions. I think, yeah, but pretty much everybody does prenorm. Okay, so to summarize, so we what did we look at? So we looked at self-attention. So what does self-attention do? So this is sort of a summary of what the transformer architecture is all about, what are the key concepts, and what you must uh, keep in mind. Okay, so self-attention, this enables distributed representations that can be learned parallelly and without issues of vanishing gradients. Multi-head attention helps you to look at different perspectives of a token. Uh, Positional encoding helps to incorporate positional information, which is lacking with self-attention and MLP. And the feed-forward network has a lot of parameters, is the brains of the network, is where the learning really happens. And then there are a bunch of tricks like residual connections and layer normalization that help to kind of train really deep networks and stack together all these different networks, both on the encoder side and the decoder side. So to summarize, yeah, you have the input, you have its embedding, then the positional embedding is added. Then it goes into the first transformer block. So every transformer block will have a multi-head attention followed by a feed forward. And in the modern architectures, you have a pre-norm. So the norm will happen before the multi-head and the feed forward. And then the output is fed to the next block, next layer, right? And so on and so forth till all the layers are computed on the encoder side. Then the decoder starts processing. So again, the decoder will sort of take these representations or representations of the output tokens and first do a self-attention, but this time it's a masked multi-head attention because you cannot look at the future tokens. Then there is a cross-attention which looks at the top encoder layer. And then there is a feed forward, right? So the only difference here is that this multi-head attention has, the cross-attention has come, and then this masking is there, right? Of course, and then the output of the uh, decoder, you will apply a linear layer followed by softmax to convert the output into a probability. And then you, if you're training, you will apply standard cross entropy loss and train the network. So that training is, the training objective remains the same, no change. It's just how the data is processed to construct these representations. That's where the transform model differs, and you achieve a very high level of parallelization with this. Okay, now there are variants, some important variants of the transformer. So what you saw just now is an encoder decoder model. So uh, and that's why it's called a transformer. Transforms an input sequence into an output sequence. Uh, but you could have the encoder part only, and that's called a transformer encoder. And there are many models, popular models like BERT, XLMR, modern BERT, and all the encoder only models that are popular, right? So, since BERT came out, they're all transformer encoder models. Transformer decoder models are very important. I mean, all the LLMs today are transformer decoder models. So they use only the decoder model, decoder part, which means they use masked self-attention. But of course, no cross-attention is needed because there is no encoder. So, so GPT and any other LLM today, they are pretty much transformer decoder model. Okay, so that's sort of summary of transformers. And the next thing you all should be doing is to dive deep to understand. So what we've talked about today is kind of an overview to understand the important concepts, and I hope you're clear about these important concepts. But then you should delve deeper into each of these, understand the math for each component, say how the attention is exactly computed, so on, right? And one very good resource is this paper called the annotated transformer. It takes the original, it's a tool, it's a website, a Python notebook, I think. Basically takes the original paper and annotates it with details so that you can understand the paper. So you should read the original. uh, Attention is not, uh, attention is all you need along with these annotations. That is very useful. If you're adventurous, you should sort of look through, uh, if you look at, say, libraries like Fair Sequence, right? So that is Meta's uh, implementation of sequence to sequence models. Uh, and you'll see some transform models there as well. So you can actually look through the definitions and see how the network architecture is being constructed so that you understand the code. Better still, you can look at Hugging Face. These days, Hugging Face is the go-to spot for transformers. Uh, So, and very well documented. There is a consistent structure to how networks are defined. So you can take any network, say Quen or GPT or Gemma, whatever, read their code of the defined definition of the code, and it is very insightful to understand and to really understand what's happening. This basically, you can just we saw the diagram for transformer, right? So you can follow what's happening in the diagram by looking through the code. Uh, then if you want to really go and implement your own stuff, train and want to learn how to train, then there are minimalistic transform implementations like Nano GPT. Uh, I'll share a reading list, and you should and maybe suggest some readings uh, to delve deeper. So there are lots of more things and advances that have happened, particularly with sort of LLMs coming in, right? Uh, you need to do a lot more things to make them efficient, right? Uh, for example, in a decoder LLM, right? So if you have a very large decoder LLM, uh, if you want to generate the next step, you need the previous what do you say encoder states at the states at every uh, time step for all the layers, right? So do you recompute that all over again? No, not possible. So there is something called KV cache, but then that has impact on memory. So how do you sort of optimize for that? So interesting thing. And then how do you sort of speed up these computations, right? So most networks today do flash attention. So how do you do flash attention? How can you quantize these models to instead of doing float 16 computation, can you do float uh, int 8, right? I mean, or even more, even smaller int 4 kind of computation. So lots of things. There's no end to think, and depending on what area you want to you are interested, you can pick up and learn more. But yeah, there are a few things you should understand and do a couple of exercises to see how well you have understood some of these things once you go through, say, the paper and understand the math. So can you sort of, if I give you an architecture, can you tell me the number of parameters in the model, right? Or what is the time and space complexity of processing a sequence? So and these are exercises for you to do and learn. Okay. Fine. So yeah, that I think closes most of the things that we wanted to discuss today. We have some time, and I'll briefly talk about the assignment. I think I'll need some more time to kind of flesh out the details, but me and Pushpak sir had a quick chat on what might be a good assignment for you guys, all of you to do to sort of learn through working with sequence to sequence models. And so. Uh, Yeah. So the whole high level idea is to sort of train your own transliteration models. So transliteration is a sequence to sequence problem where you convert text from one script to another. Say you have, uh, say the word Anand written in Devanagari script and you want to convert it to Latin script. So that is a transliteration problem. Uh, it's an interesting and appealing problem because it's the vocabulary is small, so you can uh, train these models quickly with limited compute and do lots of experiments and try out different things, right? So it's a good problem for you to do. So I think what you should try to do is build a transformer-based transliteration model, and we can have transliteration from Indian scripts to Roman and vice versa. The exact data sets and all. Uh, will work out, and I think by the end of the week I can share the details. Does that Yeah, so that's the plan, sir. I mean, you do you have anything to add, sir, on the assignment?
Oh, that will be good. Yeah.
Yeah, sure.
And
Yeah.
we should specify the levels of accuracy.
Okay.
Okay, so what is the expectation for the levels of accuracy? And what is the expectation from the reading list, from the knowledge perspective? How is the grip? Okay.
Okay, sure.
So I'll
Okay.
share a set of slides with you,
Okay.
which we normally use for other assignments.
Okay. Okay, sir.
And this template can be followed there also.
Yeah, that will be good. Yeah. And yeah, please do share, and I'll also work with Tosin and all to get the assignment up
Yeah.
and ready.
And the deadline for the assignment is end of September. I hope I'm audible to the class, Naki. Hello, Pinaki.
Yes, sir, you're audible. Yeah.
Yeah. So end of September, and as you know, this Friday there is quiz number 1 for the class, okay? And everything that has been done till today are included in the syllabus. Okay. So, is there any other question, comment from the class or from online? Any question, any comment from the class from, or online people? Okay, if not, we finish the class, and Anoop, there are not enough words to appreciate your effort and time for teaching the class.
Thank you, sir. Yeah,
Maybe,
happy to kind of talk to the students. Yeah, I think we have
yeah.
time. I had some additional topics from last time if you want to go over it, but otherwise the material can be shared.
Hmm. Yeah, I think we'll finish the class,
Okay,
and
sure.
you have covered probably the one of the most important topics in the deep learning course. Yeah.
I hope this was useful. Yeah, please. Yeah, if you have any questions, yeah, just feel free to reach out to me directly also. I'm happy to answer you. Yeah, please, students, reach out to me.
Yeah. Okay. Thank you. Thank
Okay,
you very
sure.
much.
Yeah, thank you, sir. Yeah. Thanks, everyone.
Class is over.
Okay.